When a transformer processes text, it keeps a running record of the past. For every token it has seen, it stores keys and values inside something called the key value cache. That cache grows with every new token, not occasionally, not exponentially, linearly, layer by layer. As sequences get longer, memory usage steadily rises until it becomes the dominant bottleneck. That is why long context inference feels expensive even on large GPUs. Eventually, you are limited not by compute, but by how much memory you can hold. Why does this happen? Because standard attention requires every token to compare itself to all previous tokens. Each token generates queries, keys, and values. Each head stores its own full set of keys and values. Nothing is compressed, nothing is shared. This design is flexible, but it is memory heavy. Several variants attempt to fix this. Multi-query attention shares keys and values across heads. Grouped query attention shares them across head groups. Both approaches shrink the cache, but they reduce representational richness. Memory goes down, granularity goes down, quality can degrade. So the challenge becomes clear. Can we reduce memory without weakening the model? Multi-latent attention approaches the problem differently. Instead of sharing keys across heads, it reduces the dimensionality of what is stored. In standard attention, the cache stores full high dimensional keys and values for every token. In MLA, those keys and values are not stored directly. They are first compressed into a lower rank latent representation. Only that compressed latent is cached. Later, when attention needs keys and values, they are reconstructed from the latent. This is low rank compression applied to the attention memory itself. The idea is simple. Most of the useful information lives in a smaller subspace. We store only that subspace. Operationally, the attention pipeline still looks familiar. Hidden states are projected into queries, keys, and values. But there is now an additional projection step. Hidden states are first mapped into a compact latent space. From this latent, effective keys and values are generated when needed. So from the outside, attention behaves the same. Internally, the memory representation is much smaller. There is another detail to handle: positional encoding. In standard designs, positional information is baked into the cached keys and values. If we compress too early, we risk losing positional detail. MLA separates content from position. The cached latent remains position free. When a query arrives, positional encoding, such as rotary embeddings, is applied dynamically on the query path. Position is computed on demand, not stored persistently. This separation allows the cache to remain compact while still supporting long context reasoning. Now consider the structure of a single MLA layer. Incoming hidden states branch into two streams. One stream compresses information into a latent representation. That is the only data written into the cache. The other stream computes position aware queries at full rank. When attention is executed, effective keys and values are reconstructed from the cached latent. Queries interact with these regenerated representations. Functionally, attention is preserved. Memory usage is not. What does this buy us? First, memory reduction. Because only compressed latents are cached, the footprint drops dramatically, often by more than 90%. Second, latency improvements. Smaller memory structures are cheaper to move and access. Third, quality retention. Benchmarks show MLA matching or slightly exceeding baseline attention performance. It is not a crude approximation, it is a structural redesign. So, the story can be summarized cleanly. Problem: the key value cache grows with sequence length until memory becomes the limiting resource. Conventional fixes: share keys across heads, trade memory for representational detail. MLA's solution: compress keys and values into a lower rank latent space. Store only that latent. Regenerate detailed representations when attention is computed. Compute positional information dynamically rather than caching it. Result: massive cache reduction, often over 90%, with no measurable loss in model quality. The core shift is philosophical. Instead of asking, how can we share memory across heads? Emily asks, how little information do we truly need to remember? And that reframing is what allows attention to scale further without overwhelming hardware.